Most people hear the idea of producing hydrogen without electricity and immediately imagine some kind of shortcut, perhaps a system that just heats water until it splits apart. But the real story behind thermochemical hydrogen production is far more complex. It is not about brute force heating or a miracle reaction. It is a landscape of scientific barriers, engineering constraints, and material challenges that researchers are slowly learning to overcome. The vision is compelling because it sidesteps some of the bottlenecks of traditional electrolysis. Yet this vision only becomes meaningful when we understand the obstacles facing it and the efforts underway worldwide to address them. Thermochemical hydrogen has always stood apart from more familiar methods because it attempts to do something ambitious. Split water using heat-driven chemical reactions instead of electricity. Electricity-based hydrogen depends on electrolyzers, precious metal catalysts, power electronics, large renewable farms, and extensive water purification. These components increase cost, and their availability limits deployment. Thermochemical systems promise something more flexible. If high-temperature heat can be supplied from renewable sources like concentrated solar power, geothermal reservoirs, nuclear reactors, or industrial waste streams, the system might bypass the need for massive electrical input altogether. Yet this promise is only achievable if the materials inside the system behave the way engineers need them to. At the heart of thermochemical water splitting lies a class of reactive compounds, often metal oxides, that can release oxygen when heated and then take oxygen back from water vapor to release hydrogen. The chemistry is elegant, but the materials that enable it face significant challenges. A suitable material must allow oxygen atoms to move in and out of its structure repeatedly, must maintain its shape under extreme temperatures, must resist corrosion from steam or other gases, and must do all this through thousands of cycles without losing efficiency. Many early candidates failed because they cracked during heating, fused into dense masses that reduced surface area, or required temperatures too high for practical equipment. Over the last few years, research groups have begun addressing these issues directly. New redox materials such as doped ceria, advanced ferrets, engineered perovskites, and composite metal oxides are demonstrating improved stability and faster oxygen mobility. A notable milestone came from a solar thermal demonstration in Australia, where doped ceria particles in a beam-down solar reactor successfully cycled under real concentrated sunlight. Other laboratories are exploring materials that integrate oxygen transport membranes into the reactor, allowing oxygen to be removed or supplied more efficiently. These advances suggest that materials, once the biggest obstacle, are gradually becoming more reliable. Yet even the best materials cannot perform without the right reactor system around them. Designing a reactor for thermochemical hydrogen production is more complex than building an electrolyzer. A thermochemical reactor must heat large volumes of material uniformly, maintain precise temperature gradients, circulate steam efficiently, and separate hydrogen and oxygen safely at high temperatures. It must also withstand repeated thermal expansion and contraction as the material heats and cools. When scaled up, small imperfections in design can lead to large inefficiencies. Uneven heating can damage the reactive material. Poorly controlled steam flow can limit hydrogen yield. Leaks in high-temperature gas seals can compromise both safety and system stability. To address these challenges, researchers are developing new reactor geometries, using advanced simulations to optimize heat flow, integrating ceramic linings that resist thermal shock, and testing hybrid designs that combine chemical cycling with membrane-based oxygen separation. These innovations are driving reactor performance closer to what would be needed for commercial-scale deployment. Managing heat is another formidable barrier. Because the reaction requires heat at levels far higher than conventional industrial processes, every calorie of heat must be used efficiently. If too much heat is lost, or if the system lacks mechanisms to capture and recycle waste heat, the economics collapse. High-temperature heat exchangers capable of withstanding harsh cycling conditions are under development, using ceramic composites and new insulation materials designed to reduce energy loss. Engineers are also exploring thermal storage systems that allow the reactor to maintain a stable temperature even as external heat sources fluctuate. These developments are essential, especially for solar thermochemical systems that rely on sunlight, which changes throughout the day. The source of heat itself raises significant engineering questions. Not all heat is the same, and not all sources can deliver the temperatures required for thermochemical cycles. Concentrated solar power can reach extremely high temperatures, but only with accurate heliostat fields, robust solar receivers, and clear weather. Nuclear reactors can provide steady, continuous heat, but next-generation high-temperature reactor designs are still under development and must meet strict regulatory standards. Geothermal systems offer stability, but naturally occurring geothermal heat may not always reach temperatures high enough for efficient thermochemical operation. Research is ongoing to enhance geothermal wells using advanced drilling techniques and deep rock fracturing to access hotter reservoirs. Each heat source presents its own integration challenges, and engineers are studying how different reactor architectures can match the heat profiles offered by different resources. Another obstacle lies in scaling these systems from laboratory-scale demonstrations to industrial plants. In small setups, it is easy to maintain uniform temperature and controlled reaction conditions. But when reactors become larger, gas flow, heat distribution, and material packing all behave differently. Gases may not circulate evenly, temperature gradients may increase, materials may sinter in unexpected patterns. Engineers must redesign the entire system to manage these effects. Modularization, using multiple small reactors instead of one large one, is one approach being considered, as it allows for easier heat distribution and more maintainable components. But modular systems require more complex coordination and potentially higher capital cost. Durability and lifetime testing also remain major barriers. Industrial hydrogen production requires systems that can operate continuously for months or even years. Thermal cycling wears down materials, cracks reactor linings, degrades seals, and slowly reduces hydrogen output. Accelerated aging tests attempt to simulate long-term operation, but real reactors still face unpredictable challenges when exposed to variations in heat, steam purity, and environmental conditions. Research groups worldwide are conducting multi-year experimental cycles to understand failure mechanisms and design reactors capable of enduring long-term operation with minimal maintenance. Economics will ultimately determine whether thermochemical hydrogen becomes more than an academic curiosity. Even if the science works and the engineering is practical, the cost of building and maintaining high-temperature systems must make sense compared to alternatives like electrolysis, methane reforming with carbon capture, or emerging biological and electrochemical pathways. Capital costs for high-temperature reactors, heat exchangers, solar fields, geothermal wells, or nuclear heat loops can be substantial. Materials must be replaced periodically. Heat losses and inefficiencies must be minimized. Because of this, techno-economic modeling has become a central part of current research. Analysts are studying how plant size, material composition, heat source type, regional geography, and operational cycles influence the cost of hydrogen. These models are helping researchers identify which designs are most likely to reach cost competitiveness and under what conditions. Despite these challenges, encouraging signs continue to appear. Solar thermal hydrogen demonstrations have successfully produced hydrogen under real-world conditions. University laboratories have shown repeated cycling of redox materials using focused sunlight. New redox compounds with improved stability and higher hydrogen yields are being published in peer-reviewed journals. Hybrid reactors that combine chemical cycles with oxygen transport membranes are achieving promising laboratory performance. Nuclear researchers envision high-temperature reactors as potential hubs for hydrogen production. Geothermal engineers are investigating how enhanced geothermal systems might supply steady, high-grade heat. Each of these developments adds new momentum to the field. The pathway ahead remains challenging. Thermochemical hydrogen production must prove that materials can endure thousands of cycles without significant degradation, that reactors can be built affordably at commercial scale, that heat integration can remain stable over long periods, and that the economic case for heat-driven hydrogen holds up against competing technologies. Long-term water purification strategies must be developed, as even small impurities in water can degrade reactive materials. Gas handling systems must ensure separation between hydrogen and oxygen without costly or fragile equipment. Safety systems must be robust enough to manage high temperatures and flammable gases. Yet, if these barriers can be overcome, the implications for the hydrogen economy are profound. Regions that lack extraordinary solar or wind resources but have access to geothermal heat, nuclear heat, or strong solar thermal potential could become hydrogen producers. Heavy industries that require high-temperature heat as well as hydrogen could co-locate thermochemical reactors to reduce cost and improve efficiency. Because thermochemical systems rely on heat instead of large quantities of electricity, they would avoid some of the grid-related challenges faced by electrolysis-based hydrogen plants. And since many reactive materials are based on abundant oxides rather than rare metals, the long-term resource footprint could be more sustainable. As researchers continue to refine materials, design reactors, improve heat recovery, and test integrated systems in pilot plants, thermochemical hydrogen production is gradually shifting from conceptual chemistry to engineering reality. The field's progress depends on steady, incremental advances: more durable materials, more efficient reactors, more reliable heat sources, and clearer economic pathways. None of these improvements alone will make thermochemical hydrogen succeed, but together they could create a viable new approach to clean hydrogen production. The technology is not finished. It is developing step by step in laboratories, pilot plants, and research centers worldwide. Each new material formulation, each improved reactor design, and each successful demonstration moves it forward. If the progress continues, thermochemical hydrogen could become a meaningful part of the energy transition, a specialized but powerful tool for producing hydrogen in places and conditions where electricity-driven methods fall short. The challenges remain significant, but the ongoing work shows that they are not insurmountable. The world may one day look back at these early experiments as the first steps toward a heat-driven hydrogen future, built not on a miracle solution, but on careful engineering, persistent research, and a growing understanding of how to harness heat and chemistry together in new and innovative ways.